Okay, today I will take the topic discharge through open channel by chassis formula. Okay, in steady uniform flow, the velocity, depth of flow and area of flow will be constant for a given length of channel. Already studied, see here in steady uniform flow, you know the depth of the flow, velocity of flow and discharge of the flow is constant means here the depth of flow with respect to space ds, dy by ds is equal to 0 and dv by ds is equal to 0 and dq by ds is equal to 0. Okay, here the velocity, depth and discharge is constant. So the French scientist, okay, hydrologist Anthony Chessy, he related the expressions for the discharge through the channel with a respective depth of the channel and cross section. Okay, depth of the channel, cross section and bed slope of the channel. Okay, he find out the expressions with discharge q with the slope of the channel with a slope of the channel and area, cross sectional area of the channel, okay. So already you know the longitudinal section, just check here is the longitudinal section. Okay, let us take it two sections, the one and another section 2 this is the uniform steady flow. Here the depth is not going to change with respect to length L. Okay, depth is not going to change with respect to L and this is the datum line. Okay, it makes the channel makes an angle I with the datum line. Okay, the I is very small compared to the length because I is required, the slope is required, you know, because it is the open channel. The open channel is flow due to only the gravitational force, so there will be some slope is required. Okay, so that take it as two sections, 1 and 2. Okay, see here there are some forces are acting at the section between 1 and 2. So we have to find out the net resultant forces between these two sections. Okay, we have to find out the net resultant forces. See here is the flow directions. Okay, see here the section 1 to 2, the depth is not going to change, is y. Okay, depth is not going to change, is same. Okay, so here there are four forces are acting in a section 1 and 2. The net resultant forces are acting, acting between section 1 and 2. See here this is the longitudinal sections. Okay, here section 1 and 2. You have to find out the net resultant forces. Okay, the first one the pressure force at section 1. We are going to find out the pressure force at section 1. Here there will be some pressure force is acting. Okay, you have to see here, you know, the pressure triangular. Okay, pressure force is acting at a 1/3 from the 1/3 from the base. Okay, y is same. Okay, here you know it is rho g h, instead of h you can write y. Okay, and second one, pressure force is the rho g y. Okay, the pressure force P is equal to P1 is equal to rho g y. And next, pressure force at section 2. Here also the pressure force is acting. Okay, this is the rho g and depth is also y, so P2 is also is equal to rho gy. Okay, the P1 is equal to rho gy at section 1 and pressure at section 2 is also rho gy. Okay, third one, component of the weight. Okay, component of the weight in flow direction, because here we're going to consider only in a flow direction. See here, this is the component. See here, the weight is acting exact vertically downward, and the component is here the vertical direction. Okay, it makes an angle I, so it will be W sin I, and here it will be W cos I. So while resolving the weight, the horizontal component is W sin I. Horizontal component means it is along the directions of the flow is W sin I, and perpendicular to the direction of the flow is W cos I. Okay, perpendicular to the direction of the flow is W cos I, and along the direction of the flow is W sin I. One thing is, here only W sin I is causing the flow of motion. Okay, so only we are going to consider the component of the weight in the directions of the flow, in a flow directions. Okay, the fourth one, there is a friction force is acting against the flow of the motion. There will be a friction force is acting opposite to the directions of the flow, F. Okay, the friction resistant force is acting in the opposite directions of the flow, Okay, the friction resistance force is acting in the opposite directions of the flow. The first force is pressure force at section 1 and second, this is here pressure force at section 1 and pressure force at section 2 pressure force at section 2 and component of the weight in flow direction. This is the component of the weight, W sin I is the component of the weight in the flow directions. Okay, next fourth one is the frictional resistance force is acting the opposite direction of flow. Okay, the frictional resistance force, see here, this is the longitudinal section, here it is a cross section. Okay, see here, you know, the when water is flowing in the direction, okay, in the x direction, if it is flowing in the x direction, the opposing frictional force is acting at the periphery. Here, this is the perimeter. Okay, acting at this surface area, wetted surface area, acting at the wetted surface area. How to find out wetted surface area? This is the wetted perimeter into the length of the channel. See here, just take it as this is the channel. Okay, just take it as this is the channel. So this is the wetted surface. This is the wetted surface complete from here to here. Means if it is here up to here, it is the depth of the water. Then we're going to find out this is the wetted perimeter, and this is the complete area. This complete area is called as a wetted surface area. Okay, so here the friction force is acting in a wetted surface area and in the opposite directions of the flow. Okay, then what are the parameters we are going to consider here? There are different parameters we are going to consider in the section. The first one is length of the channel. Okay, L is the length of the channel. Okay, the L is the length of the channel. Okay, and W is the weight of the water between the section. Okay, between section 1 and 2. Okay, is the weight of the water. Okay, is the weight of the water between the section 1 and 2, but we are going to consider only W sin I because this is the in the directions of the flow, the components in the direction of the flow, it causing the motion. Okay, so here the next it is V is the mean velocity of flow. See here, the velocity is constant here because it is uniform steady flow. Okay, the velocity is constant, and y or d, whatever you can take it as a depth of the flow. Okay, just take it as a y. Okay, is the depth of the flow. Is the depth of the flow. This is the d or y, you can, or y. Okay, whatever you can take it as. Okay, y is the depth of the flow, and F is the frictional resistance per unit area per unit velocity. Okay, the frictional resistance per unit area per unit velocity. So the L is the length of the channel, W is the weight of the water between the section 1 and 2, V is the mean velocity of flow, Y is the depth of the flow, and F is the frictional resistance per unit area per unit velocity. Okay, over. Next we are going to find out the net resultant force. The first one is the pressure force. pressure force at section 11. What is the pressure force? Pressure force at section 11 is rho g into y. Okay, rho g into y. Y is the depth of the flow, and in pressure force at section 22 is also rho g into y, the pressure rho gh or rho gy. See here, these both are same, these are both equal in magnitude but opposite in direction. See here, it is opposite in direction. The pressure force, the P1 is acting in the direction of flow and P2 is acting in the opposite direction of flow. So here the pressure force at section 11 and 22 is cancelled each other. Okay, the pressure force P1 and P2 are cancels each other because pressure force are equal in magnitude and acting opposite to each other. Okay, the equal in magnitude and acting opposite to each other. So here pressure force P1 and P2 cancels each other. Okay, next third force. What are the third force? Okay, third force are the weight of the component in the direction of flow. Weight of the component in the direction of flow. Okay, weight of the component in the direction of the flow is W into sin I, right? W into sin I is the weight of the component in the directions of the flow. Okay, W, okay, is the weight of the flow. Okay, weight of the liquid or weight of the water. So how to find out the weight of the water? See, the unit of the weight of the water is Newton, right? So how to find out the weight of the water? W sin I. Okay, W is the weight of the water. How to find out? See, the weight, okay, is in Newton. So you can find out the density. Okay, density into volume. See here, it is kg per meter cube into meter cube, so it will get in kg, right? So we need in Newton, right? The weight is in Newton, so into acceleration due to gravity is g, right? You will get in a Newton into sin I, right? See, W into sin I. W is the density into volume into acceleration due to gravity into sin I. So density is the rho. Okay, rho into volume is, how to find out the volume? Okay, volume is area into length, right? Wetted perimeter, wetted area into length. See, this is the volume. Okay, into acceleration due to gravity g into sin I. See here, the volume is the wetted area into length. Wetted area means, see, this is the wetted area. Okay, see here, okay, is the, just take it as a cross section of the trapezoidal. So this is the wetted area. Okay, just take it as a 3-dimension. Okay, see, okay, this is the channel. Okay, so this is the area. Okay, the water flows, this is the cross sectional area into length, this is the length, so you will get the volume. Okay, wetted area into length, you will get volume. So finally you can write the equations. Okay, equation you can write it. The W sin I, the weight of the component in the flow direction, you can write